Okay, yeah, again, thanks for coming. I thought I'd come here and introduce a project that I've been working on for about 6 months or so, and something that has been under discussion now for a couple of years. This is actually the first time this is being presented, so it's a work in progress, and this is the first main overview that's been given. So the goal of the project is to improve the security of Linux virtualization, and I think it's good to state a kind of an achievable goal. Note it doesn't say fix security or solve security, just improve it. And by Linux virtualization for the sVirt project, I'm talking about a specific form of virtualization. Now, there's a lot of different terminology that's used in virtualization, and there's nothing standardized. I checked with all the virtualization guys. There's no kind of standard term for this that I'm aware of. So I'm just going to refer to it as Linux virtualization, where the hypervisor or the container controlling the virtual machine is actually just a normal Linux process. And I'll get into why this approach is being taken as I get into the talk. So there are several examples of this type of virtualization which I guess most people will be at least familiar with. There's KVM, which is the QEMU project enhanced with support for the virtualization capabilities of the Intel and AMD chipsets. So this is basically just a normal, or a reasonably normal Linux process that runs in user space and contains the entire guest kernel and guest user space. There's also lguest. Rusty's hypervisor runs completely in user space. And there's also UML, and there's probably others. And these are the type of virtualization that sVirt is specifically targeting. So this is a conceptual diagram of this form of virtualization. It's generalized. There's each particular flavor of virtualization will have slight differences, but this sort of at a high level covers all of them. And as you can see, we have the host hardware with a single kernel, and then we have several guests. And in this talk, I'll generally refer to guests as being the virtual machines, just to try and be consistent. And each one of these vertical blocks is just a normal process that you can start and stop and kill and assign resources to and so on. And there's a kernel running inside each process. So this type of virtualization is particularly compelling in Linux because it means that you can reuse a lot of the existing Unix mechanisms or Linux mechanisms that already exist for process management. You can apply to virtual machines, and you don't need to build a whole new infrastructure. And this is one of the reasons why KVM, for example, is of interest to people. You don't have a separate hypervisor with a separate set of tools. And sVirt basically aims to extend this concept to security. So we have a lot of really good security mechanisms in Linux, and the idea here is to try and identify some possible security threats that can be applied to virtualization, and then use the security mechanisms that Linux has to try and mitigate those threats. So that's sort of the basis of why we're just addressing these types of virtualization, the process-based virtualization. So you should be trying to use, so if you're deploying KVM or UML or these types of virtual machines, you should be trying to use discretionary access control as much as possible. There's a lot that you can achieve with DAC, which is what I'm referring to here. You can use chroot, you can use different UIDs to separate them, you can set permissions on the resources they have. We've now got namespace support in Linux so that you can clone processes off and they're isolated and their networking's isolated, and so on. So that needs to be done, and that's good. One of the issues though is that discretionary access control, or DAC, is often considered to be inadequate to meet the needs of modern security threats with the globally networked environment. And There's a really great paper that the original SELinux developers, the NSA researchers, published called The Inevitability of Failure. And this basically outlines really well the case for why you need mandatory access control in addition to discretionary access control. So I can't go into the depths of that paper, but it's definitely worth looking up if you're interested in security. And the basic underlying problem is that subjects, which in security terms refers to active entities such as processes and users, which are just using processes. The problem is that they have discretion over their own security, and essentially they can modify their own security characteristics. So the canonical kind of example of why this is insufficient today is that you might have, say, a web server or some sort of internet-facing service which has a bug in it. Now, all software has bugs, which I think any developer will agree. This is something that you assume. Some of those bugs will be potential security issues. They can be vectors to attack. So if you had a web server that had a bug in it that could be exploited remotely, you might then find that the remote attacker in on any part of the globe for any kind of motivation will be able to, say, execute arbitrary code just depending on the attack and the limit of it. So the problem is with DAC that once the application has been breached, then any privilege that the process was running with can be delegated out and used, and also it can set permissions and so on its own resources and possibly do things that it wasn't supposed to be doing. There may not be anything stopping it from accessing the network to send mail, for example. And even though you think you've locked it down without a coherent system-wide security policy, you don't know what sort of channels that the attacker might find to get out. So part of sVirt is to try and leverage mandatory access control in locking down Linux virtualization. And the difference with mandatory access control in the way that it's implemented in things like SELinux, it's not necessarily the traditional definition, but essentially a subject can't bypass the security policy of the system. So you have a security policy which is centrally administered and enforced at the kernel level in this particular implementation. And so if the web server is breached remotely, then the attacker is quite limited in what it can do to bypass the system-wide security policy. So of course if the security policy is weak, then there may be ways out. But because also the security policy is being enforced at the kernel level and it's being applied to all of the security relevant accesses, you can have a complete picture of the security policy of the system. Okay, so in terms of virtualization, I guess everyone knows that virtualization's been around for decades and that it's nothing new. But in terms of security threats, I don't think we really have a complete picture yet of what the threat model is for virtualization as it's being deployed on the internet and as we're getting into grid computing and cloud computing in particular. So this threat model is a work in progress, and this is just something that these are some issues that we've identified that we know about that we can address and hopefully improve security in some meaningful way. So I think down the track we'll learn more about security and virtualization in the internet, and we'll have to revise some of these threat models or at least extend them and address new issues as they come up. So virtualization, maybe the statement isn't completely correct, it can introduce new security risks, but I think we need to be assuming that it does. And there's a paper that's been published, I think it's called The 5 Immutable Laws of Virtualization Security, and it goes through, I'm not sure how immutable they actually are. It's like some research group came up with them. But in particular, when we're talking about using virtualization to consolidate services that were previously running on physically separated systems, we can introduce new security risks because now we have services running back on the same physical hardware again. So you can actually improve security through virtualization. If you had a bunch of services running and you virtualize them on the same system, you're putting an operating system container around them, so you can improve it, but it can also introduce new security risks. So the main model that we're looking at with sVirt at this point is the flawed hypervisor. Now, because the hypervisor, the virtual machine, runs just like any other process, it basically has the same or very similar attack profile to all the existing process-based threats. And what you're looking at is the scenario where you have a malicious guest. Now, it may not be installed for malicious purposes. It may be compromised after being installed if you're running a virtual hosting service, or you have a system on a virtual host. Someone might break in and install a rootkit, and if there's a flaw in the hypervisor, when they break out, they can then potentially attack other guests that are on the system and potentially the host as well. So this is the main threat model that we're looking at this stage. So before people were using virtualization in this way, we had systems that were, as I mentioned before, that were physically separated. So you might have a data center, you might have a DMZ, and a good practice might be to have, say, a set of servers with each running a separate service locked down particular to that service. And then you say, well, we want to consolidate this hardware into one system. Well, firstly, here's a diagram of this initial scenario that I mentioned. And as you can see, we have on the left side a system which is just running a web server, and it's been locked down really well. On the right side, a DNS server, and this is in your DMZ or DMZ. And if the web server is compromised, and the attacker can get out and execute arbitrary code, possibly find a privilege escalation attack to get root or whatever, they can basically own that machine. But to attack the DNS server, they basically have to go through the local network to attack. And if you've got really good local network security, and I'm not sure what the state of the art is in switches, it's been a while since I did any sort of sysadmin work, but I'm pretty sure that you can plug these systems in directly into firewalls, and you can use MAC security to make sure they can't see each other and so on. So the attack, even if, and a good thing would be to actually make sure that these systems can't actually see each other on this network as well, or at least find each other. But in any case, the attack surface here refers to, which is a term which refers to, I guess, the amount of, the size of the surface area of the attack that you can make. The attack surface here is fairly narrow, it's fairly small, and it's basically limited to the network. So after virtualization, if you consolidated those two services onto one machine, you will have your DNS server and web server running on the same system, on the same physical system. And the way that a lot of virtualization is actually deployed by default, they'll be running as the same UID. So it's a good idea with DAC to try and run them as different UIDs. And I think in Fedora now, if you install a virtual machine as an unprivileged user, it will actually set it all up with your own user ID. But now we have one system and one kernel and one piece of host hardware. So if this attacker now gets into the web server and they get out into the host user space, they now can start using local exploits. And all existing local exploits on the system will potentially be available to attack this DNS server next door. And also, they may be able to access resources that are owned or used by the other server. So if it's using a disk image and they're running as the same UID, there's not really even an attack. They can just read it, modify it, so on. And this is also a particular problem if this is running as UID 0, and I think if you go and look, a lot of virtualization schemes are running as UID 0. It can do all kinds of things. So the attack surface has expanded considerably here to the same old exploits and vulnerabilities that you had before isolating them physically. Okay. So hypervisor vulnerabilities. Now, when I first started working on this project, when I first started thinking about it about 2 years ago or so, I wasn't aware of any vulnerabilities in hypervisors or virtualization. I'm sure they existed, I just hadn't heard of them. And since starting this project, I think 3 or 4 major vulnerabilities have been published. I think there were 3 in one day by the same people at one of the Black Hat conventions last year, and these were related to Zen, I think. So a slightly different model, but this proves that they're not theoretical, and I'm assuming that if people are publishing 3 or 4 in a year, there's maybe a few more that haven't been published. So it's an evolving field, and I think that from the point of view of people who in this industry of finding exploits and either selling them or publishing them, that some of the older avenues have progressively dried up. Some of the memory-based attacks and remote root things have been, there's been a lot of improvement here, and virtualization is a field which I would imagine would be fairly ripe for looking for new types of attacks. And also the payoffs, if you can compromise a hypervisor, the payoffs are potentially huge. You may have, on one system, you may breach one virtual machine and then get access to 10 or 100, and depending on the type of virtualization and the type of hardware, there could even be eventually thousands of systems that you just simply can pick off at will, and entire company networks and so on, without leaving the machine. So this brings us back to sVirt. So this was just a lead up to introduce what sVirt's about. And the idea of sVirt is relatively simple. And the idea is just to take the mandatory access control mechanisms that are now available in Linux, such as SELinux or SMAC, and use that to try and confine and protect some of the virtual machines that are, or guests that are running on a host. And the idea essentially is to contain hypervisor breaches in the same way that mandatory access control can be used to contain breaches of normal applications. So the question of where to implement sVirt is interesting, because virtualization, there's tons of different types of virtualization solutions, and there's quite a lot of potential complexity. So there's a library called libvirt, which is a virtualization API. Just wondering, people familiar with libvirt? Just need to know how much detail to go into. It's an abstraction layer that was developed by Daniel Viard, who's famous for his work with XML, and also some other developers, Daniel Barange, mostly at Red Hat initially. And the idea is that it's a way of allowing applications to interact with virtualization through an abstraction layer without having to be aware of all the different types of virtualization, so that the management tools and monitoring tools and the layers such as oVirt, it's a web-based virtualization enterprise management system thing, it can actually go through libvirt and not have to worry about the different types of technologies that come along, and they are evolving relatively rapidly. libvirt currently supports Zen, KVM, also QEMU without KVM, Linux containers. There's various types of Linux containers that come under the term LXC, openvz, and a few others, I believe, UML. Okay, so this is just a very much simplified diagram of libvirt. And the reason it's simplified is because some of it's not really relevant to the discussion, and also mainly because I can't fit it on the screen. So as you can see at the bottom here, there's some applications. Virsh is the virtualization shell. virt-manager is a graphical tool. And they basically plug in and work with a standardized API. And there's actually some RPC going to the back end, so this can be put over a network and secured with TLS and various things. I've left that out because it's, again, doesn't fit. And within libvirt, there's this concept of drivers. And as you can see, there are drivers for different types of virtualization, which they call hypervisors. So you have a Zen driver, a KVM driver, openvz driver. Some of these virtualization systems have their own APIs, so it's basically a wrapper around their APIs or their management systems. Some of them don't, and QEMU and KVM were previously quite difficult or I guess brittle to manage yourself, and it's now with these tools it's quite easy to manage some of these systems. Excuse me. There's also drivers for storage. You can use libvirt to manage storage for virtualization, and these again they're plug-in. You can plug in different types of storage drivers. There's also network drivers which I haven't shown. And then libvirt then looks at what the connection URL is that you're using. It makes extensive use of XML and URLs and RPC, and figures out what type of hypervisor and where the host is and so on. So you can actually be working with remote systems or local systems. And we have a example of a host here with a particular type of hypervisor and various guests running there, and also different types of storage. So this is a kind of a very high-level view. It's a little bit more complicated once you peek under the covers. So the idea with sVirt is to basically follow this general architecture and to build in a pluggable framework in the same way that there are pluggable frameworks for disk, for storage and for different types of hypervisors, and to be able to support different types of Mac labeling schemes such as SELinux, potentially SMAC, and others that come along. And the role of the security driver in sVirt is essentially to manage labeling of resources. So we want to be able to put security labels on the disk and various other resources that a guest is using, and also we want to be able to label the guest itself because it's a process. We can put a security label on it. And then the security policy is enforced by the existing mechanisms by the kernel, and we don't have to have a new security mechanism in place. This is really just a kind of a labeling driver for virtualization. So I've now expanded the libvirt diagram here to show the security drivers which can be plugged in, and I've been working on the SELinux driver so far. There's a test driver which basically does nothing, which hopefully at some point will form some sort of useful test suite. And what we have here is where I've put stars or asterisks is where we have security labeling information being built into the API calls. So, and also I've changed the colors on the guests and on the storage to indicate that they're running with different security labels. And the security labels can be anything. sVirt, even SELinux, to a large extent actually doesn't care what the label is. It can be whatever you want it to be. You know, you could have, these labels could be labels of different companies, departments, security levels, whatever you want. And so if you're running, say, virt, when you look at to see what guests are running on this host, the labeling information will come back over through the API and back out to virt, and it will display it. openvz is probably not compatible with sVirt, with this particular type of security driver. It's not a... So libvirt actually still has these other virtualization drivers, but sVirt doesn't necessarily work with them. And we've actually had a bit of a discussion about this, and it may be useful to do some... the sVirt API, we're still keeping an eye on potentially being able to convey labeling information and security information for other types of virtualization, but it's not being designed in that way. But so some of the design goals of sVirt, I'll just cover the main ones. And probably one of the main ones is the idea that we're reusing code that's been proven, it's already been written, debugged, it's been out in the field, there's tens of millions of people have used it and attacked it. And this is basically the kernel mechanisms in SELinux, for example. What we do with sVirt in terms of that is just change the security policy to cater for it. But we already have existing code and also security models. We don't have to come up with new types of security models, whereas for other types of virtualization that are not process-based, you would need to invent a new type of security model and write new code, or at least port code, which is actually being done for other types of virtualization, and I'll mention those at the end. The other thing is that because of this, we actually get the ability to have a coherent security policy which covers the entire system. So the same single security policy which is being applied to protect system files and being used to protect from external attacks is the same security policy that is confining the guests, the virtual guests. And we can then analyze and reason about the behavior of the system as a whole, and we don't have a separate virtualization security policy which we need to try and connect up. And overall this reduces the complexity of the system as a whole, being able to reuse these components, and that's a really good security design goal to have in general. I don't think anybody would disagree with that. And also it reduces the cost in terms of we don't have to do a huge amount of new development, which means it's more likely that it'll actually happen, and that the quality hopefully will improve from that, and also should reduce the cost to the end user in terms of training and integration and so on. And yeah, with lowering the cost of security to the end user, hopefully makes it more likely that they will adopt it, and the more people that adopt it, the better it will become. And so one of the primary design goals of sVirt, it's got its own slide, is something based on a lot of hard lessons that we've learned with SELinux. In particular, the idea of just dumping a whole bunch of pieces in the user's lap and say, well, it's really great, go and do something with it. It's not necessarily the most optimal approach to providing security to people. So one of the main things is that I want sVirt to be usable. Like if people have seen kiosk mode, I gave a brief demo of it the other day, something that is just easy to use, and also something that is actually useful and doing something that you can demonstrate tangible benefits of it, so that it's not some esoteric idea and it's not some conceptual thing. You can actually say, well, if you switch this on, it'll actually help you. So from those design goals, we get on to the implementation goals of the first iteration. And we're hoping to make a 1.0 release this year and get it into Fedora. So initially we just want to provide something called simple isolation of guests. So there's actually quite a lot you can potentially do with sVirt. You can utilize all kinds of interesting concepts of allowing controlled flow between the guests and so on. Well, in this case, what we want to do is just make a release where if you switch it on, it just isolates the guests from each other and they can't attack each other. And so that's a fairly simple goal. From a policy point of view, it's fairly simple as well, or relatively simple. We also want to aim at zero configuration. We don't want people having to go in and modify files or understand SELinux policy. I don't know if we'll get to zero. You may get to a point where when you're installing a virtual machine, it may ask you, you're installing a guest, it may ask you if you want it to be an isolated guest. The other thing is that if you're actually running SELinux in enforcing mode, it may make sense just to do it as a best practice. We have to sort of trade off whether this is going to cause people problems or not, and whether this can lead down some of the previous issues that we've had. And something that came from Daniel Viard, who I think is not a great fan of SELinux. He wants it to be debuggable and to have a good debug loop. And this is something that we can do. There's a audit subsystem in the kernel which is hooked up to SELinux, and libvirt, which is a daemon which controls all of the guests on the system, can basically hook into the audit system and look for its own process IDs for its own guests. And we also have a facility called SETroubleshoot and SEAlert, which analyze AVC messages or policy violation logs and try to tell you what's going on. So we can actually, and this is a plug-in based system, we can actually write some specific plugins for virtualization to help increase that debug loop. So we're basically trying to make something similar to kiosk mode in terms of usability. So I'll be concentrating on the initial SELinux implementation here. As mentioned, sVirt is not SELinux specific, so this is just one way of doing things, and this also only is only covering the simple isolation goal, and there are other things that can be done. So you can use different types of security models, and within those models you can, particularly with something like SELinux, which is has a lot of flexibility, you can have different types of policies. So the main idea with simple isolation will be to simply ensure that each guest has a unique security label. And it doesn't actually matter too much what that label is, just as long as it's unique on that particular system. And then the security policy can be applied based on the difference, to differentiate based on the label. And SELinux security labels are a whole kind of talk in themselves, but in this case I've vastly simplified them to show two components which policy will be applied to. On the left side is a type, and on the right side will be, we think probably we'll just use the UUID of the virtual machine, because it should be hopefully unique, which will be, for those who understand a bit more about SELinux, which will actually be an MCS category set mapped to a UUID by the system. So what happens with the type on the left side of the label? Broad behavior of the guest will be applied to this security type. So all of the isolated guests will have the same set of rules applied to them, and this applies to broad behavior such as what types of disks and resources and objects they can access and how they can access them. And this will actually start off being the existing type, which is, you know, for non-isolated, and we're not sure yet whether we need to make any more changes to that. There's already a pretty good policy there. And then for the simple isolation mechanism, there'll be a unique component on the right, probably the UUID, and there'll be a very simple clause in the security policy which will basically say that all accesses between those different UIDs are denied. They're just completely isolated. There's no communication between them, and it's the aim here is to try and restore some of the isolation that you had when they were physically separated and reduce that attack surface. Now this is sort of, I guess, like firewalling the virtual machines from each other. You can think of it a bit like that. And because with SELinux all security relevant objects and accesses between them are mediated, and because it defaults to not allow any access, essentially we just remove any possible accesses that may have been allowed by previous policy. So it's actually from a mechanism point of view and from a policy point of view, it's actually quite simple conceptually. You're just saying if the labels are different, they can't communicate with each other, they can't read each other's memory, they can't read each other's resources. We also need to label the resources appropriately as well. And one of the properties, I think in the 70s, a really good paper was one of the sort of foundational security papers outlined a series of desirable security properties, and one of these properties is simplicity of mechanism. And while some aspects of the security mechanism are considered complex, this conceptually I think is quite simple. So here we have an updated version of the diagram that I had before, where you have two guests running on a system, say using KVM, and notably the colours have changed to indicate different labels. And we have our web server on one side, the DNS server on the other side, and I couldn't actually fit UUIDs in the diagram, so we'll just pretend that the UUIDs can be just integers, 1 and 2. And as you can see, we have the web server is running inside a process. In fact, the web server and its kernel are running inside a process which is labelled virt-D isolated T, which just tells a policy that it's an isolated virtual machine, and it wants to do virtual machine type things, and the one basically says, well, it can't actually talk to anything that doesn't have that one or that UID attached to it. And as you can see also, I've included their disk images, and of course they may not be disk images, they may be logical volumes or NFS mounts or various things that can be labelled. But for simplicity, they'll just be disk images, and these images have also got a type label and also labelled with the UID of their owner. So we just have a policy which says that the virtual machine, if it's going to access a disk, then it has to have the same UUID. And SELinux is plugged into sVirt, and through the driver mechanism, it's also operating in the host kernel. And so now if this web server gets compromised remotely and they come out and try and attack and get to the virtual image of the other system, or just go and read the memory, go and dump the process and feed it back out through the web server, whatever the attack is, the hope is that SELinux will then block that attack. So this is obviously idealized. If there are flaws in the policy, or someone finds a bug in SELinux or something, then obviously there may be a way around it. But this is basically the enhancement to the security that we're aiming for. So there's quite a lot of things that we can do in the future with this, and we definitely want to keep it simple to start with and try and achieve these simple goals of just isolating the guests and having something that's usable and useful and people are happy with and go, hey, this is cool, I'll switch it on. But we can also start doing things like changing the label and having different types of isolated guests. So we could say, well, do you know if this is going to be a web server or not? If so, we'll actually tighten the policy down so that you can only do web server type things, like the virtual machine will actually be confined, for example, to web server ports that are defined by the administrator, 80, 880, 8080, 443, and be able to use DNS and so on. So there's some potential there to do further lockdown. And beyond this, there's, I guess, an almost unlimited amount of things that you can do. One which may be of interest later is the ability to have controlled flow between different guests. And this might be, for example, if you want to run a typical sort of DMZ with, say, a front-end web server which is doing rendering of HTML, and behind it you have, say, an application server which is pumping XML across to the web server, and you might have a database server, so on. So you may want to be able to say, well, we want these systems to only just talk in this way and not any other way on the in the virtualized environment. This would require, I think, some really high-level tools, such as perhaps being able to graphically draw lines between the system and automatically generate policy. Definitely don't want admins having to go in and manually type in the policy, although we won't stop them. In fact, they could just adapt sVirt and do that if they really wanted. We're also potentially looking at virtualized network security. So now with these tools, with virt-manager and so on Fedora at least, and I think Ubuntu is adopting some of this as well, or has adopted it. We have things like a bridge that the VMs connect to, the guests connect to, and we can look at having like a virtual network on the system where you can start enforcing IP tables rules between them. We can start looking at putting security labels on the network packets to actually label the traffic between them, ensure that the correct labels are on the traffic, and also start looking at using crypto and IPsec on the virtual machine. There's quite a lot of things we can do there to provide increasing amounts of security. And also there's an application here for traditional multi-level security where you have guests running at different security levels, and this is something that is, there's already some solutions already doing this in various ways with Linux. So ultimately this may be applicable to that kind of use. Some of the related work that is related to this project, there's a labeled NFS effort going on, which the code is mostly written. This is to try and put security labeling into the NFS version 4 protocol, and that's going through the IETF process now, which is fairly bureaucratic. labeled networking. There's various types of ways of assigning labels to networking in Linux, and that support is essentially done now, although I don't think it's very usable yet. And also looking at embedding this type of idea into the X server. There's the XACE project, which is a bit like LSM, where you can plug in different security models into X. So we can start looking at extending all of this out to both the desktop and out to the network, so all the way through the distributed application stack and across the network. There is something similar in terms of applying mandatory access control to virtualization. There's a scheme called XSM, the Xen security modules. This is similar to LSM in the kernel, where you can plug in different types of security models into Xen, and there's a port of the Flask architecture which underlies SELinux to Xen. That's a bit different, and in fact this is an example of the approach that we're not taking, and with that they had to port software across. In fact, one of the vulnerabilities that was presented at Black Hat was because some Linux kernel code was ported into the Xen hypervisor, it was safe and tested in the Linux kernel, but it wasn't safe in the Xen hypervisor, and it was a different calling convention or something that actually led to a breach. So they also have their own management tools and so on, and their own infrastructure. It's not a criticism, it's just a different approach. And also the aims of the XSM SELinux stuff are a little different, in that Xen-based virtualization has this all-powerful DOM0, which is a bit like the root user, and they want to decompose that into different drivers running in different domains, and to be able to deprivilege some of the DOM0 functions. And also there are several proprietary schemes, as I mentioned, and they don't necessarily generalize to the extent that we're hoping that sVirt will, and obviously by the virtue of the fact that they're proprietary, we don't exactly know what they do. So currently the low-level integration has been done. I've developed a prototype. It's been posted out and had a few iterations on the libvirt mailing list, which is very promising because those virtualization guys really know their library pretty well, and they're fairly happy with the design of the pluggable security drivers thus far. You can configure it to put a label on a guest, on a KVM guest, and then you can launch it with this new security label. And there's also basic support for labeling in virsh, which is the virtualization shell tool, which is like a command line interface to libvirt, and you can query the virtualization daemon and see what security labels the different guests are running, what security models, and whether they're in enforcing mode, and so on. So we're at a point where we've got proof of concept, kind of consensus from upstream, and it's now, the project's essentially now being handed over to real user space developers who know Python and how to integrate things into Fedora. So Dan Walsh, who people may be familiar with from SELinux, is now working on this too. And the main thing that we have to develop now is this simple isolation mechanism. So that's why some of it was, well, we expect it to work this way, but it hasn't actually been proven yet. So there's a project page if you're interested. Everything, you don't really need to write that down, you can just Google for sVirt. Google will probably insult you and question your English language skills and tell you that you've probably spelt it incorrectly. You haven't, just fine. I think it's in the first few results normally. And there's links to all of the code drops and the design documents and so on. So I think we've got just a very brief amount of time for questions. And I'll be outside later as well. Casey.
Okay, so what are your plans with regard to commonality of policy among the machines involved? If you have, for example, running SELinux on 3 guests and on the host, you would want to have some commonality of policy between them.
Yeah, that's an interesting general problem, and it's, you know, what do you do with policies that are different on different systems? So thus far, what we're expecting is that the policy will be configured on the guest, and the role of And we may actually end up be looking at deploying security policy through libvirt. There's been some work in the Traces folk have done some work in deploying and distributing security policy, and there may be some of that down the track. But initially, it's just the security policy is local, and all you see currently over the API is just the labels, and it will just render them into something readable. So we don't yet have the ability to say translate between different policy environments, and the policy will be local to the machine that it's running on. But that's a very good long-term research question.
Yeah, it sounds like a really good way of adding some defense and depth to the problem of virtualization. It seems a pity to have to create a new user identity for each virtual machine. Is it possible to solve the problem using virtual?
Yeah, so, okay. So the question is that it's difficult, I guess, to use different user IDs for different virtual machines. So that's discretionary access control, and that would be a recommendation. I think some of the KVM people have recommended it. Currently, if you just install system, there's two different types of guests which will be installed if you run the latest version. They're called session virtual machines or session nodes or something. That will be done as an unprivileged user, and it will be set up in your home directory and so on and run as your user. But system domains will probably all be running as UID 0, so at the very least you want to run them as an unprivileged user. But ideally, because if someone breaks out and they're running as the same user ID, you might have a bank running something on in one container, and Joe Random Quake server running on another one which has got some hole in it, and someone breaks in and goes, "Oh, if I get out of here, I can see what's in the container next to me." So, yeah. So the idea is that with mandatory access control, we can actually separate them using security labels. So even if well, we would recommend using both, but because user IDs are controlled under discretionary access control, if there are local exploits on the system which allow you to bypass this stack security, of which there are many types of exploits which may have actually been forgotten because they're not useful anymore, may become useful with virtualization, right? It may not have been useful for a long time to be able to just simply attack some random application on the system that you've broken into, right? Because you can't do anything with it. But if that application happens to be an entire virtual machine with hundreds of users on it and financial information, it's a different story, and suddenly these local exploits are effectively like root exploits, because you're getting into root on a virtual machine that's running in a process. So there's definitely some new security threats here, and part of the idea here is to try and address those. So I think we're basically at the end. So is there? Okay. Well, I'll be around if anyone's got questions. And
just one more thing. Thanks for your time that you've given for your lectures. There's your bag.
thanks. If you want.